Hi friends, today we are going to learn on the greedy method single source shortest path, that is Dijkstra'S algorithm. Remember that on the greedy technique earlier we have learned minimal spanning trees by using Prim's algorithm, Kruskal algorithms and greedy knapsack, job sequencing problems. This is Dijkstra'S algorithms is to find single source shortest path. Say, as for example, we have cities called Hyderabad, Bangalore, Delhi, Mumbai, right? And we wanted to find shortest distance, right? So maybe there will be a vertex from source to destinations, right? Say it is 2000 kilometer, but there is another way, right? Say via Delhi, to go Delhi from here, I will go via Hyderabad, right? And distance, it can be like from distance from Bangalore to Hyderabad, Hyderabad to Delhi. Maybe some of the distance will be lesser than direct distance. In that case, we'll go with the direct distance. This is our tendency. This is our greediness, right? Always we'll go for the shortest distance, okay? Or in other way, you can say that in a lesser amount of time to reach to destinations from the source. And in similar way, you can see that nowadays it is very popular when you are going to travel, right? Easily you are going to see that what is that Google map, right? We'll start and we'll see that what is the destinations, and when we'll fill, right, start the journey, right, we'll be getting the different path, right? Someone will be based on the distance, someone will be based on that time taken to reach. Right, it is up to user which path you are going to follow. But here basically we are going to discuss based on distance, or you can say cost matrix, weighted matrix, right? It means that for Dijkstra'S algorithms we should have graph called weighted graph, and in previous session we have discussed already what is weighted graph, right? What is weighted connected graph, right? So here you should have cost matrix, cost from A to B, B to C, C to D kind of things. So we'll discuss with an example. So now in this we can see that by seeing this statement, single source shortest path, right? Say as for example, if we have city A, we have a B, we have a C, and we have a D. Okay. Now, say these all are the age, right? In a real life, what will happen, friend? Distance, right? Path. So here, all path from city A to city C, we are going to mention through age. And say from city A to city C, it is a 5 kilometer. So we are going to say that cost is 5. Similarly, A to B, it is 10 kilometer. B to C, it is 20 kilometer, right? Similarly, A to D, say we have a 7 kilometer. D to A, we have a 6 kilometer. Here we can say that each and every connectivity path, we have certain cost. That is called weight. Okay. Hence, this kind of graph is connected. Yes. Each and every edge of the graph is having certain weight. Yes. Hence, it is called weighted connected graph. So remember that Dijkstra'S algorithms or programs, we are supposed to give the input in the form of graph, right? But we are not able to give input exactly in the form of graph. So we are going to use representation of graph. Representation of graph means what? We are going to write same graph in the form of adjacency matrix. So how many different vertex we have? We are having A, B, C, D. A, B, C, D. Remember that here A to A, when we are talking about source to source, as we are sitting at your home and you are saying that what is the distance from my home to home, right? It is remain 0. So diagonal A to A is 0. A to B, since it is undirected graph, so A to B and B to A distance is same. So A to B is 10. A to C 5, A to D 7. Similarly, B to A. Remember that A to B and B to A. Since there is no direction on edge, hence we can call it as A to B and B to A. Both are same. Hence B to A we can say it is 10. Okay. B to B. Again, what is that? B to B. Source and destinations are same. So 0. B to C is 20. B to D, there is no path. All of you please see that. There is no direct path. I am not saying there is no path between B and D. No. Direct path from B to D. Do you have it? No. In that case, it is called it here in graphical term infinity. But in a keyboard, we don't have infinity. Right? It means we are going to see that what is the cost matrix we have, and comparatively these all values we are going to give larger values. So at the place of this infinity we are going to give here say 999, right? It looks like very large values compared to this, or you can write it infinity for our understanding. Okay, now C to A, similar way it is 5, C to B is 20, C to C, source and destinations are same, 0, and C to D is 6. D to A is 7. D to B, there is no direct path, hence it is 999. D to C 6, and similarly D to D 0. So you can see that diagonal elements are 0 where source and destinations are same. So when you are writing the programs, when I and J, right, both are same, it is diagonal element, and those values will represent here 0 in a cost matrix. So let us see. If you see friend here, B to C or C to B, B to C, what is the direct distance? 20. But if you go from B to A and A to C, what is the distance? 10 plus 5, 15. It is less. So we will not go with the direct path B to C, we can go by B to A and A to C. Means it will give you path called 15 if B is a source vertex. Right? Similarly, do you have any other shortest path in this? A to C will remain 5, right? A to D will remain 7, right? When you are talking about B to D, B to D, B to D you don't have direct path, but there is a path B to D 20 plus 6, 26. From this way, B to A and A to D 10 plus 7 is 17, right? Hence, or we can say B to D 10 plus 5 plus 6, it is 21. So 26, 21, 17. Which is lesser distance? 17 is lesser distance. So like this we are going to find shortest distance. But in this particular problem statement, it is mentioned that single source. It means source is fixed. So in Dijkstra we are going to fix the source, and from source we are going to find all the remaining vertex. So if we have a 4 vertex, then we will be having 3 paths, A to B, A to C, A to D, if A is a source. If A is a source, we are going to find distance A to B, A to C, A to D. If B is a source, B to A, B to B, no sorry, B to A, B to C and B to D. Like this we are going to find the distance. What are the points? Are there single source shortest path problem? For the given vertex called source in a weighted connected graph, as I mentioned it, find the shortest path to all other vertices. In a 4, I said you that from source to all remaining vertex. Applicable to graph with non-negative weight. Very important. Non-negative weight. Remember that friend, weight can be negative or positive, but our Dijkstra'S algorithms works for non-negative weight only. Now why call it as a non-negative? You would have written positive also, right? But positive means what? It is, right, 1, 2, 3, 4, 5 positive integer. If you wanted to include 0, then you have supposed to write non-negative. Okay, so non-negative weight, it means what? 0 is also included. Find the shortest path to a graph vertices in order of their distance from the given source. First, it finds the shortest path from the source to a vertex nearest to it, right? That is called greediness. First, we'll go in a neighbor. If I have A to B, A to C and A to D, among this, which is the lesser distance, we'll go to that vertex first. A to B is lesser, or A to C is lesser, or A to D is lesser. First, we'll visit that particular vertex having the lesser distance from the source. Then to second nearest and so on. These vertices, the source and the edges of shortest path leading to them from the source form a subtree Ti of the given graph. I will discuss about this, friend, how it is formed trees, right? Remember that we have discussed earlier that tree is what? A cyclic connected graph where number of edges will be one less than the number of vertex. Next vertex nearest to the source can be found among the vertices adjacent to the vertices of Ti. Those vertices are referred as a fringe vertices. So let us see that how exactly we are going to perform the task in Dijkstra'S algorithms, and thereafter we will discuss how to write the algorithms. All right. So say if you have a vertex A, we have a B, we have a C, we have a D, and we have a E. Right? Say we have a distance here 2, 1, 3, 6, 4, 3, 4. So cost is already given on each and every edge. And in this case, say we are going to consider A as a source vertex. A as a source vertex. Then what will happen, friend? We are going to perform by applying Dijkstra'S algorithms. Hence, we are going to write the cost matrix of this to give the input to the programs. So, similar way as you have discussed earlier, we will be having A to B, A to C, A to D, B to A, B to B, B to C, B to D, B to E, C to A, C to B. We are going to write all the cost matrix. Now, since source vertex is already defined, so here we are going to write for discussion vertex. Okay, we are talking about remaining vertices, vertex and remaining vertices. And last part we are talking about illustrations. As we have discussed in the previous concepts also, illustrations, or you can say that to discuss one by one how exactly things are working. If A is a source vertex, first we are going to write A. Okay, A is a source vertex. Now from A, what is the distance from A to other vertex? So here we can see that A to B distance is 2. So we are going to write B, A, comma. Now A is a source vertex here. As I mentioned, A is a source. So we are going to write A to C. Do you have direct path from A to C? No, we don't have direct path. Hence, you are going to write C, right, dash infinity, right? Or if I mention here C, A, comma infinity, that is also all right. A to C distance is infinity because you don't have direct path. Similarly, A to D, do you have direct path? A to D? No, we don't have. So just you are writing D hyphen infinity. Then A to E, do you have path from A to E, where E is the destinations? A to E? Yes. What is that? It is E. A to E is 6. This first part, and we are going to see that what is the minimum distance what you have computed here? 2, infinity, infinity, 6. From A, we have two possibilities. Either I can go to B, or you can go to E. But as greedy method says that we are going to prefer having the lesser values because you are going to find out the shortest distance, not the maximum distance. So among these 2 is minimum. Hence, we are going to reach from A to B. We are going to visit vertex called B. So B is A comma 2. We have already selected. It means at this point of time we are at B. And in illustrations part, since we have A to B already selected, we can write A to B is already selected and path is 2. Clear? And that is why we are talking about the T of I. Right? We are going to construct this trees and that will give you final shortest path. Now we are at B. From B to A, no, we are not going to traverse back. A vertex is already visited. We are not going to revisit it. So we are going to visit all new vertex which is listed over here. Look, A to C we don't have direct path, but B to C there is a direct path. B to C there is a direct path. So we are going to write C. Okay. B to C, what is the starting vertex, end vertex? B to C there is a path. So we are going to write B. But point to be noted here is we are going to find shortest path from the source. So A to C, what is the distance? A to C via B. A to B already traveled and B to C is 1. So it is 2 plus 1 is 3. We are not going to write 1. We are going to write 2 plus 1 because distance we are computing from source. So A to C distance is 2 plus 1, 3. So here we are going to write 2 is already computed plus 1. All of you please concentrate on this point. It is B to C distance is not 1. We are writing 2 plus 1 because it is computed from source. Similarly, D. Do you have path from B to D? Direct path, do you have B to D? No. So in these iterations, D will be remain unknown. It is infinity. Similarly, now we are at E. Look, A to E, there was path, direct path is 6. All of you please. A to E, direct path is 6. But if you go via B, A to B that already computed and B to E is 3. So 2 plus 3 is 5. 2 plus 3 is 5. Direct distance is 6. So we are going with via B. That is distance is 2 plus 3. So we can write here B to E. Distance will be 2 plus 3. Now here we can see it is 2 plus 1 is 3. Here is infinity. And here is 2 plus 3 is 5. So of course 5 is lesser. So we are going to take it out. We can see that here B to C is 2 plus 1 3, where B to E is 2 plus 3 is 5 and here is infinity. So if we see whole from A to C is 2 plus 1 3 and A to E is 2 plus 3 is 5. Among these 3 is minimum. Hence C we are going to take it out. C B 3 and rest of the vertex D and E we are going to recompute it. So at this point of time we are at C. Okay, we are at C. Now we can see that if we are at C, then there is a path from C to E and there is a path from C to D. That is both are we can compare it because already we are having A, B, C. So two new vertex D and E is unknown. So we are going with the D and E. So let us see that the D. and we are at C. So what is the distance from C to D? C to D is 4, but distance from A to C is 3 plus 4. So distance from A to C is 3. We have written here B because via B, but distance from A to C is 3 and C to D is 4. Hence we can write 3 plus 4. For vertex E, if we go via C, then it is A to B, B to C is 3 and C to E is 3. So 3 plus 3 is 6. But what is the previous distance? 2 plus 3 is 5. So 5 is lesser than 6. So you are not going to update it. You are going to write E, B, 5. Among this, 4 plus 3 is 7 and here is 5. Of course, 5 is lesser. So we are going to take it E, B, comma 5. And we are going to, of course, we are not joined it. So it was 1. Now B to E we have done. That is distance is 3. We are at E. If you see that E to D there is a path that is a 4 unit. And distance till E is 5. So 5 plus 4 is 9. But previous iteration, if you see that C to D is 7. So if you are going via A to B, B to C and C to D, it is 7 unit. While A to B, B to E and E to D, it is 9. So of course 7 is lesser. We are not going to update it. So we are going to write C 7. And finally we are going to update D of C comma 7. And here we are going to write C of D, that value is 4. If you see this complete graph, right, actually you can draw this one by one. Each and every iterations, just join one edge and finally we will get the final graph. Okay. Now we are going to conclude how you are going to write it the distance. What was the source? Source was A. What is the distance from A to B? A to B is 2 unit. What is the distance from A to C? A to C, you can see that C vertex, it is a 3 unit. A to D, you can see that D, what is the unit here? What is the weight here? Total distance is 7. And A to E, what is the distance A to E? We can see here, all distance we can find out here. 2, 3, 5, 7. So it is, E is 5 unit, right? Fine. So this is the single source shortest path A to B, A to C, A to D and A to E, all the distance were computed. If person will ask what is the sum of or cost of these minimal spanning trees in this kind of graph like Dijkstra'S algorithms, we are going to write all this sum of all the values. 2 plus 3 is 5 plus 1, 6 plus 4, 10. 10 is the sum of complete this path. Otherwise, this is your final answer for Dijkstra single source shortest path. Let us see that what are the things we have done it. Input is a weighted connected graph G, V, E for non-negative weight. As I said you that 0 is also included. Shortest path from source S to all other vertex, and in previous example source we have taken as a vertex A. Distance of V for each vertex V in G, distance of V is equal to infinite, right? It means what? We have initially all the vertex we have considered as a infinite, and previous V is equal to null. Just we have a 2 points we have taken it. Initially we don't have any vertex, right? We have considered as a null. If V is not equal to S, vertex is not equal to S, remember that we are not going and calculating A to A, B to B, C to C and C to D. If A is a source vertex, we are not going to compute A to A path, right? V to pivotage Q. Initially, distance of source is equal to 0. It means what? S is your source vertex, and as we are given the example that distance from your home to home is remain 0. So just we are initializing that distance of S is 0. After that, what you are supposed to do, if while Q is not empty, right, extract mean from Q. Extract mean from Q. It means we are going to find out the minimum values and we are going to put it in U. How it is? In first iterations, we are going to find the minimum values A to B, A to C, A to D and A to E, which is a minimum, right? Here also we have discussed that, right? If you see that first attempt, what is minimum? In first row, A to, if A is a source vertex, then A to B, A to C and A to D. What is the minimum? 5 is the minimum, because we are going from A to all the vertex, 5 is the minimum. Similar way, here if A is a source, we have considered that A to B, A to C, A to D and A to E. Which is minimum? A to B. 2 was minimum, so we have taken out. So that distance we have computed here, right, and put it in U. It means that is the vertex we have selected here, right. For each unvisited neighbors V of U, unvisited means what? If you are at B, then unvisited is what? C, D and E, right? So those vertex. Remember, indirect distance you are going to compute, right? And what is indirect distance? Distance of U plus edge weight from U to V. All of you try to understand this part. Very important. Distance of U plus edge weight of U to V. So in this particular case, you would have noticed, right? If direct distance we already computed here in this particular case, right? Infinity, infinity, 2 and 6, we computed 2 is minimum, we take it out. Now, indirect distance means what? A to C was infinity. We don't have direct distance. Indirect distance means via B. So we are going to A to B and B to C. So look, we are at B, say positions is, we are at already B. If you are at B, then what is distance from B to C? 1. So distance from A to B is call it as a U in your algorithms. Okay. And from here to here, B to C, that you are going to compute the distance from U to V. So sum of the distance D of U plus weight of U comma V. That is what? 2 plus 1 we have computed here 3. Here 2 plus 3 we have computed as a 5. Right? Similar way, we are going to represent this as a distance of U plus edge weight from U to V. Now what we did, friend? In previous example, I said you that if 2 plus 3 is 5. In this case, in E case also, 2 plus 3 is 5. But what was the direct distance? Direct distance was 6. Indirect distance was 5. So we have updated with indirect distance. We have updated with indirect distance 5. Similarly, A to D, we don't have direct distance, but we have updated with indirect distance. In each and every iterations, we are going to compute indirect distance and compare that indirect distance is lesser than direct distance. If indirect distance, what you have computed, dist of U plus edge of UV is lesser than direct distance, then indirect distance we are going to update as a dist of V, means that is the minimum distance based on greedy method, right? And that particular vertex we are going to put it in arrays called previous of V, since we are going to write all the input in one arrays. So just to mention that this is previous of V is equal to U and return distance and previous, right? So basically it will give you that final graph what we have done it in previous example. So this is the final source to all the vertex and distance. Yeah. So this is all about your Dijkstra'S algorithms. Now we can see that what will be the conclusion or summary of Dijkstra'S algorithms. Remember, Dijkstra'S algorithms is to find single source shortest path using greedy method, and time complexity of Dijkstra'S algorithm is E log V. What is E? E is a number of edges present in the graph and V is a number of vertex. So it is E log V is the time taken to perform the task in Dijkstra'S algorithms. All right. Thank you.